Have you ever looked up at a bridge, or maybe the roof of a stadium, and just wondered how that intricate web of steel can be so unbelievably strong? Well, we're about to pull back the curtain on the brilliant secret behind one of engineering's absolute greatest designs. It really all boils down to this one question. I mean, how can something that looks so, well, so empty, be way stronger than a solid chunk of metal? It seems impossible, right? But the answer is, frankly, a stroke of genius. So let me introduce you to the truss. Its whole job, its entire reason for being, is to take all the complicated forces acting on it and simplify them. See, in engineering, bending is the enemy. It's an inefficient way to handle stress. The truss brilliantly gets around this by making sure every single piece is only ever being pushed or pulled. And that is what makes it so incredibly strong for its weight. Okay, so to make this whole thing work perfectly, at least, on paper, engineering is the only way to do it. Engineers start with a really simple, idealized model. Let's just call them the 3 golden rules. Okay, first rule. Imagine all the joints are these perfect, frictionless pins, kind of like links in a chain. They can't transfer any twisting force. Second, all the weight and forces are only ever applied right at those joints, never in the middle of a beam. And third, every single piece is perfectly straight and totally weightless. In this fantasy world, you get pure, unadulterated strength. But we all know the rules. The real world isn't perfect. It's messy. So what happens when this elegant, clean theory has to get its hands sturdy? Well, in the real world, pretty much every single one of those golden rules gets bent or just flat out broken. And that changes the whole game. Remember those frictionless pins? Yeah, forget them. In the real world, engineers use these big, rigid, welded things called gusset plates. And here's the problem. Because they're rigid, they don't just transfer a clean push or pull. Oh no! They let those unwanted bending forces sneak right back in, creating what engineers call secondary stresses. And it doesn't stop there. You've got the beam's own weight, because nothing is actually weightless. You've got loads that get applied in the middle of a span. And on top of all that, the connections are never perfectly lined up. All these little imperfections pile on, bringing back the one villain the truss was designed to defeat, bending. And the impact here is huge. Get this, a tiny 4-inch offset. Now, how a joint's connected, they call this eccentricity, can reduce the truss's total load capacity by a staggering 21%. That is not a small number. So, does all this mean the ideal model is just useless? Absolutely not. This is where the real engineering magic happens. It's all about a super clever 2-step philosophy. Here's what they do. First, they actually use that simple ideal model to quickly figure out how to make a truss work without the main push and pull forces. It's fast. It's effective. It gets them in the ballpark. Then, in step 2, they go back and add in all that real-world messiness to calculate those extra bending stresses and make absolutely sure the final design is safe. And that really is the key takeaway here. That perfect theory isn't wrong. It's an essential first step. It's this brilliant tool that turns an impossibly complex problem into something solvable. It's a beautiful dance between the ideal world of theory and the ideal world of theory, and the messy, complicated world of reality. Subscribe for more.